Good afternoon. The slide is visible.
Yes, sir.
Okay. So, in the last class, we discussed about the k nearest neighbor, and then we saw that there is a problem if the dimensionality of the data points is very high, and that is called curse of dimensionality. And then we have shown that how actually this problem can be handled. Okay, so today we start another very fundamental, very naive kind of supervised learning approach. It's called Bayesian learning. Now, this Bayesian learning is basically based on a very naive and fundamental statistical theorem called Bayes theorem. As you all know, is Bayes theorem. So, before starting, since it's another very fundamental kind of approach, so first off, we again just recapitulate the problem. What we are basically trying to do in our supervised classifier. So, for any supervised learning problem, we have a set of examples. So that is the level data. I repeat this thing quite a few times because this is very important to understand that these assumptions are very important. And there is a hypothesis class. Sorry, it's called hypothesis class. So what do you mean by hypothesis class? That a set of suitable hypothesis function, or I should say the HF. Just for example, you can say it's a linear regression, or linear curve fitting, or a polynomial curve fitting, or a neural net, or a SBM. So this is the kind of class. Okay. So function h from a hypothesis class h such that h of xy. So you can say h of x1 means x1 is this x1 is basically a sample of data sample that may be 1, 2, dot n kind of. This is the next. This will going to give you a y1. Y1 means given. So what is x1, y1? X1 is a vector of a particular dimensional feature space. So if feature is basically, let's say, if it's n dimensional feature space, so your xi is basically xi1, xi2, and this one the xi n. So this is n dimensional feature space. So this is the vector. Basically, that's why it is bold, and the corresponding level. So class level or class belongingness. So this is your training, and it is basically which space? This is a d-dimensional space, or better here better to say d. Okay, so then it's a d-dimensional space. So, and it is C. C is a class, and this H belongs to H. So this is the notational uh, expressions, or is a notation used for this. So then we can understand that that is a possible of competing hypothesis. So maybe you can see that if this is this kind of is there. So there may be different kind of hypotheses like this, and we have to choose according to the our loss function. So we have to find out the probability of the individual hypothesis given the data, so that we can find out which is the most probable or most likely happens. Now you see here, what we found here, it is that the this kind of is called kind of linear regression concept. We use a uh, least square or square sum or noise square um, error will be minimized. Now here we have used a different nomenclature, different terms. So what? And we have to find out the probability of the individual hypothesis. You see, the probability of individual hypothesis given the data. So probability of a hypothesis given the data. So that is somewhat maximize or max. So this is the kind of concept that for H, this is maximized. Okay, we'll come. Just don't say anything about it. We'll come what is this. So that we can find out which is the most probable or most likely hypothesis. Okay. So this is very important here. In our Bayesian setting or Bayesian learning, we'll see this particular thing. So in Bayesian learning, we'll see how this can be computed using the Bayes theorem. Okay, so this is very important, that will come up this particular thing. Okay, so let's start with Bayes theorem. So what is Bayes theorem? Bayes theorem is very easy to understand. That's the probability of a function given as some data. So this is the probability, can be written as P of the given the function or hypothesis, what is the probability of data, and we say that given this hypothesis, what is the likelihood of the data, that we can say. Then this is H, the likelihood of the function, hypothesis function, and this is the PD, that is the likelihood of the data. Or you can say prior of hypothesis, prior probability of the hypothesis, and prior probability of data. We'll see later also what is the meaning or implications here. Now, how can we prove it? So what is the proof of this? Very easy proof. As we all know, that we can say the theory of joint probability. If of H of D, we can easily write P of that. That is the definition of probability. This is okay. This is the definition. And same thing, if we say the indefinite thing, DH, we can say P of D, P of H of D. And you can see these two things. These two things basically are the same. These are two equals. This equals, so that we can write P of HD, that this fellow is basically equal to P of DH, this into P of H by PD. So this is exactly the proof of this particular base. This is very easy to prove. So since this is this, we get the base value. I think nobody has any kind of doubt or any. If you have anything that you have a kind of concern, please ask. So otherwise, it's a very straightforward. Okay. Now, before going to just try to understand how this kind of Bayes theorem can be used for a different application. So let's say we have an application that we are basically trying to find out a particular you can say value driven example. That means let a person takes a lab test for gluten allergy. Now gluten allergy is a very important, and Djokovic has gluten allergy. Now it become world famous before this. So this like a gluten allergy, and the result comes positive. So this is just a fact. Now, given the result is positive, we have to calculate the probability that the person has a gluten allergy. That what is the probability that person has the gluten allergy? That we have. So it given is a positive, that is given, and what is the probability that this person is allergic? Allergy. Allergic. That we have to find. And at the same time, given the positive, what is the probability that this person is not allergic? So this is the not sign. These two things we have to calculate. तुम्हारा just for example, तुम्हारा कोई टेस्ट लैब टेस्ट करके हो just for COVID. So positive आया है, but positive आया है how much? So RT-PCR is not always a very accurate test. There is a, let's say, there is a some percent of accuracy. Here also same thing. So what we have following data. So data probabilities. Using the Bayes theorem, we can calculate the above probabilities. So what is given? The test returns a correct positive, the true positive. Correct positive is very, it is very, now the true positive. It's a very, everybody, I think we are very, it is very familiar. Positive result is 98%. So it is very accurate, but in our artificial is not that much accurate. Anyway, of the cases in which the allergy is actually present. So true positive. So what do we mean by true positive? That means it is given true and it is given allergic and it is true. This probability is 98. Okay. And if it is this is 98, what is the false positive? It is definitely 1 minus 98, 2.98. So this is 0.0.02. And what is about that? The correct negative result is 97%. So correct negative means what? That it's a negative and patient is not allergic. So this is 0.97. So this is exactly this particular. So if this is so, when it is a basically false negative, that is 1 minus. This is basically how it is, 1 minus 0.9. So this is 0.03. So these two also you can understand. Okay. Furthermore, the 0.8% of entire population is allergy. So if we have the how many total जो population है, उसमें कितने का total allergy है? So this allergy, so it is called the allergy is 8.8% में 0.8 by 100, so 0.008. Okay, and not so then it was not allergy. 0.992. So it is 1 minus 0.008. Same thing. Okay. Now you can understand everything, that what is the value. Okay. Now these two values you can very easily calculate using the Bayes theorem. What Bayes theorem said? If allergic is a given positive, what is the probability allergic? This we're calculating this. That is exactly giving allergic. What is the probability that is actual positive? P of allergy. How many people? And by PD. P of the positive. It is basically जो the total data है. So this now what is the probability of this? And what is the allergic? It is that given positive. What is the probability that per patient is not allergic? That is P not allergy given P given not allergy. What is the probability of the positive? And P of not allergic by P. Now you see you can cancel out PD because PD is basically a constant. It doesn't mean anything. So here you can just put the value 0.98 into 0.0008 and 0.03. So it is that 0.0007. So this is the probability that the person has the allergy. Okay. Even it's good positive. And what is the probability that when it's not allergic? It's 0.02 or 0.03 you can say. Probability that the person has not the allergy. Got the point? So this is the way you can the various application can be easily done by this application. This is a probabilistic. So if you have any question, you can ask. Okay. Now we have some sort of notation or nomenclature kind of. So you can say some notation. What is called these probabilities? So this probability that this the given data. Now you please see that given data, that is actually our problem. Given some data samples, okay, so data is given. What is the probability of a hypothesis function? So that is, so exactly this is called, since this called, this particular thing, this thing is called posterior probability. You please remember this. This is called posterior probability. Give data is given, what is the ये data जानने के बाद what is the probability of each? That's why it is posterior. Okay. Now this probability P of DH. Now hypothesis is given. So this hypothesis is given. Now what is the likelihood of the data to be generated on the basis of this hypothesis? Okay. So if we have a kind of hypothesis function, then let's say this kind of hypothesis. What is the probability of data that have been generated? So likelihood of the data of that data being generated if the hypothesis H is true. This is the probability. So it's a sometimes it's called likelihood of the data given the hypothesis. And what is pH? It's called what is the probability of this hypothesis, that how much is it's popular, or how much it's probable. So it's called prior probability. It's a hypothesis prior. Sometimes we say that a lot of different priors we have used for our machine learning data extraction or kind of feature extraction. We said the prior. So this is the prior probability of the hypothesis. And this, what is PD? This is also a very complex. So what is the prior probability of the training data? Now it's sometimes said that there is some sort of noise or something. How much probable the data is? You should not say that how much accurate it is, that what is the probability of the data. So it's a data prior. So prior probability of the training data. So these are the very important thing. So the H is prior probability of the hypothesis H or class prior probability. This PH is basically that. PD, prior probability of training data, or predictor or probability. So these are the names actually. Sometimes don't be confused if they give you the name. P of H given D, probability of the H given D, it is called a posterior probability. That is it. It's a posterior probability. And D given H, probability of the D given H, which H is hypothesis is true. What is the likelihood of the data to be being generated? Likelihood on chance, kind of chance factor, you can say. Okay, so these names are often used interchangeably in our discussion. Okay, so this is an important thing, important slide. You have to remember these things. Okay, now we understand what is linear regression. Okay. So where linear regression, what do we mean by learning? That we understand. Logistic regression. What do we mean by learning? What do we mean by linear regression? What do we mean by learning in case of linear regression? To know what? Anybody?
Learning slope and the y-intercept.
MMC. So that means, or you can say theta 0, theta 1, same thing, parameter. Very good. So here also same, kind of. So what is KNN? What is been my learning? The kind of, you can say, distance functions and the this particular assumption, that similarity kind of. Okay. Now here, what do you mean by learning? So can Bayes theorem be applied to find a suitable hypothesis? Okay. Now that we have to try to find. What do we mean by Bayesian learning? So here we say we called a maximum a posteriori. So this framework we want to learn. That is called MAP, maximum a posteriori. It's a very, very important thing. That finds a most probable hypothesis that describe the data set. Okay. So most probable means what? So say that most probable means that kind of, I should write is argmax of H, probability of H given D. So I'll come in that how actually it is being given. So it is, now you see that we know this is the Bayes rule, the Bayes theorem. Generally, we want to most probable hypothesis given the training data, that is a map or map hypothesis. This H map is basically that argmax where that is an H belongs to hypothesis form class. So that this P of given B, this hypothesis is maximized. Okay. So that we have just written in the last slide. This is called H map, maximum a posteriori probability. Okay. That we are going to learn. If we can learn this, we can understand that particular hypothesis we're going to choose. Okay. So the hypothesis we are going to choose in case of linear regression by a parametric model. Here we can use a probability value. So that is the maximum. This hypothesis function has the maximum probability given this. And definitely this hypothesis function H belongs to our hypothesis cluster. Hypothesis space. Now you just use the base theorem here. So just tell this PhD use base theorem. We can say what is P d of H, P of H by P of D. This is the base theorem. Exactly, this is written here. Now this D is a constant because it is not depends on this hypothesis. Because it's the data, whatever data we don't have any control as a hypothesis. So we can neglect this. So we can get argmax of H belongs to hypothesis space H, P of D given H. So this is the H map. That is maximum as to that we are trying to understand in this particular Bayes theorem or Bayes learning. Okay. This is the very naive kind of definition, fundamental definition. Now another case we can see here, if for all hypothesis function, अभी ये जितने सारे hypothesis function इसके अंदर है, if all are equally likely, so equal have an equal probability PHS, so this probability of H are equal. Okay, so that is for any two function within this class H, Hi is equal to Hj, for I not equal to J, that we can further simplify this particular H map and we call it then we call it is maximum likelihood. But you please understand this maximum likelihood has the assumption that this hypothesis function are equally likely. Okay, if this is so, then we can say that H of ML is argmax, this P of D of HI. So this HI, so any HI you can take. So this we can omit this time. Okay, so this is the expression of the maximum likelihood, and that is we use very frequently in our different vision or machine learning applications. Maximum likelihood estimate, MLE, the maximum likelihood estimated or something like that. All these things. So important thing, the wide prior probability of the all hypotheses are equal. Okay. So this is the definition. So this is the two very important definition. This is definition 1 of map. This is the definition 2. ML. That will be very, you have to be very careful. Now, okay, now we take the example that how this kind of definitions are going to work in a real life situation. Okay, now we go back again our linear regression example. So linear regression, so that the linear regression, I will represent this linear regression problem in a bit different way here. So here we say learning a real valued function. Now it's a real valued function only because you can say the linear regression, real valued function, because this is basically x and this is fx, and this fx is a real valued in case of linear regression. So here we say we learning a real valued function. So you know when it's regression, this is the real value. This y-axis or fx, this is the real value. So here any function, any point here, we can get this function. So that's why it's a real valued function. Consider a real valued function, target function f. So the target function f is basically that f we are trying to estimate. That is what you understand. This f is we are trying to estimate. It's not predicted. This is actual function. Okay. Now to represent this f, there is a training examples are given xidi. Now this training example is not always a very accurate, because in a practical situation these are not very accurate. So this di is noisy training value. So always there, not training values, training samples are not always accurate. And generated by this di is basically defined if f of xi. So this f actually we are trying to plus some noise. So it's epsilon I. This is basically epsilon I. Okay. So now you can see here this f. Let's say f. This f is this. This is this straight line. This is f. This solid straight line, and there is an error. This solid straight line kind of this actually this is kind of error they have. We can say this error. So this is the noise associated. So this noise. Now, how we define this noise? How much noise it is? Okay. So this EI is basically a noise drawn from independently from each. So this noise is independent of each xi. So what I'm trying to say that xi, x1, there is a noise E1, x2 and E2. This noise, these two things are not dependent. All are independent. So the noise drawn independently for each xi follows, and this noise follow a Gaussian distribution or normal distribution, you can say, with mean 0 and the standard deviation or variance I square. Standard deviation, that means sigma square is equal to 0. This is the noise distribution. Okay, the noise distribution is something like this. So this is a very common way, statistical way that this particularly follows the noise with the Gaussian noise. Okay, so we think that dy is coming from a normal distribution whose mean, this di is coming from normal distribution whose mean is f of xi and error variance is sigma square. So this is basically, this particular sentence is very, you can say, we can write in this way, di. So it is very important. This di actually what is basically a normal distribution where f of xi is the mean means, and there is some sort of variance because of noise, and noise variance is okay. So this is the basically the data, this di is actually. So these data points are now very accurately represented by this noise as well as this actual function f. Right? So for geometrical, or you can say that is the mean kind of thing, and there is some variance of this, and so that we can represent the data points very accurately in the presence of noise. Here, sigma squared is a variance of the error term. That's definitely that this error, because this is the variance, how far it is distracted from the mean. That is the now, as the noise drawn from independently from the individual instance, so that I said again that this way I can say that noise are basically independent of these instances. They are data instances or individual instances. So this is the setting. Now you know how the data is being distributed. So now what is our target? Our target is basically to predict f is that actually, don't confuse, f is the actual function. So what we are actually, we have to try to find h. So that is we use the h of ml because we try to find out the maximum likelihood estimator of this H such that it can approximate F. So that is our goal, to find out this H using some maximum likelihood, whatever we have seen. Okay, now see what to do. So we have to find H which estimate F. How to find it? We use the max ML hypothesis. So what is our ML hypothesis? H. So H of ML, we just learned this is argmax. H belongs to this, and this is the probability of D given H. Okay. This H's are equal probable of something because this is ML. Okay, so this is H of ML. An assumption is this. Now, what we'll do? There is some mistake here, so I just rewrite this. H of ML is argmax. H belongs to this hypothesis class H. This is probability H given D. So this is the ML, the standard ML formulation. Now, what do you mean by this? So there is a data sample, M data sample. Let's say there is a M data sample. So in the probabilistic setting, we have to multiply each data sample. What is the probability of that? So then what if you say that this is argmax, H belongs to H. This is the multiplication. Okay. As y into n p of di. D now I said don't D. Di means instances of given this H hypothesis function. So वो H hypothesis function use करने से every data instance को हम लोग कैसे probability. So probability of every instance. Okay. Now what does this instance, this PDI, what we write? This part is equal. So here we can say, we can write argmax H belongs to H. This is the capital pi 1 to m. Now what is this? This is a, how it is done? It's a Gaussian distribution. It follows a Gaussian. So I write a Gaussian distribution 1 by root over 2 pi sigma square. This is a normal Gaussian distribution saying writing minus of. So it is basically, you can say, di minus h of xi. So these are the difference by sigma x square. This is a Gaussian distribution, normal Gaussian distribution. Okay. Since di coming from the normal distribution, it's a normal distribution. Now we put a log because it's a exponential function. Maximize the natural log of this instant. So here what we put, that we put this part, we can put a log here. So it will come argmax. H belongs to H. And you since it is basically a multiplication term. Now if we put a log, multiplication terms become summation terms. So you put a summation here. Is equal to 1 to m natural logarithm 1 by root over 2 pi sigma square, and ये minus आ गया minus half di h of xi by sigma square. So this is the term. Now there is a one mistake here. Actually, this particular term you see is there is no h. So there here you can say this is no h constant. So it's a constant, and it is not doing anything to that. So what we write that argmax वहाँ पे एक गलती है. That should be a 1 argmax. So it is a minus half. That is okay. So we ये जो I is equal to 1 to m ये लिखना. There is one mistake. So that this is the thing. So it is the argmax. H belongs to H. It means class. The summation I is equal to 1 to n minus half di hx I by sigma square. Okay, so this is the thing. Now you see, now this sigma square is also kind of constant because it's just this thing. So we can write argmax h of this minus di h is I whole square. So we can say that again it is there is a mistake. So argmax h belongs to h. This is also a constant. So you can write also. It's not a if you are one. It's a half I is equal to 1 to m di h xi. So this sigma is all sigma square we can omit because it is a normalization term. Okay. Now are you familiar with this? What is this? Now argmax big there is one mistake. There is a minus here. So then it is the argmax. So it is basically now it belongs arg mean because this is minus sign. H belongs to H half segmentation I is equal to 1 to n di minus h of xi whole square. So this is the thing. So are you familiar with this? What is this? This is the loss function of linear regression. Okay. Now you see that this is the, you can say, the Bayesian explanation of loss function or the linear least square regression. Get it? This is the way that we come up with this particular. So if you have any question, you can ask. So this is the least square criteria, which is the linear regression. For this hypothesis function, the cost of the function is minimize the sum of the square distance. This is the Bayesian explanation of the linear least square fitting. What I write there. Okay. Now you see how much it is very. So this Bayesian thing is how much powerful. That these things explain your that this linear regression explains very nicely. If you have any question, you can ask. Otherwise, we stop here today, and next day we will start optimal classifier, Bayesian optimal classifier.